examples, and basic problems. Chapter 13. A comparator with hysteresis is also called the Smith trigger. The trigger points are found by applying the voltage divider rule. The upper trigger point is R2 divided by R1 plus R2 multiplied by V out max, and the lower trigger point R2 divided by R1 plus R2 multiplied by negative V out max. What are the trigger points for the circuit if a maximum output is plus 13 volts, negative 13 volts? Upper trigger point R2, R1 plus R2 multiplied by V out max. If you apply that values, you find the value there of plus 13 volts. Multiply plus 13, that gives you 2.28 volts. By symmetry, the lower trigger point would then be equal to negative 2.28 volts. The input signal in figure A below is applied to a comparator in figure B. Draw the output showing its proper relations to the input signal. Assume that the maximum output level of comparator is plus 14, minus 14. So first of all, we know that the reference voltage is set by R1 and R2. V reference is R2 divided by R1 plus R2 multiplied by positive V. So apply that formula, you will get a value there of 1.63 volts. There you can see basically how the output is going to look like. There's your input signal, there's your output signal. At 1.63, it's been triggered. 1.63 there, it's been triggered to a negative direction. So basically, each time the input exceeds plus 1.63, the output voltage switches to plus 14 volts. At each time the input exceeds negative 1.63 volts, the output switches to negative 14 volts. By changing the ground reference to negative 5 volts, another useful circuit is formed. The input is a 4-volt peak triangle wave, minus 4 volts to plus 4 volts. The output is a square wave that delayed by the amount that it depends on the settling of R2. What are the upper and lower trigger points when R2 is set to maximum? The upper trigger point, R2 divided by R1 plus R2 multiplied by V out max. That gives you 100K divided by 127K multiplied by plus 5, and that gives you plus 3.94 volts. Lower trigger point, symmetrical, negative 3.93 volts. A summing amplifier has 2 or more inputs. Normally, all inputs have unity gain. The output is proportional to the negative of the algebraic sum of the inputs. So let's do the example. What is V out if the input voltage is plus 5 volts, minus 3.5 volts, and plus 4.2 volts, and all resistance is equal to 10K. So it's unity gain. So you can say it's plus 5, negative plus 5, minus 3.5, plus 4.2. If you add it all up, you get a value of negative 5.7 volts. An average amplifier is basically a summing amplifier with a gain set to RF divided by R is equal to 1 over N. N is the number of inputs. The output is a negative average of the inputs. So if you look to this example here, what is V out? If the input voltage is 5 volts, minus 3.5, 4.2, assume R1 is R2 is R3, is equal to 10K, and RF is 3.3 kilo ohm. So we apply the formula there that V out is negative 1 over 3 multiplied by V in 1 plus V in 2 plus V in 3, and that gives you a negative 1.9 volts. A scaling adder has 2 or more inputs, with each input having a different gain. The output represents the negative scaled sum of the inputs. Assume you need to sum the inputs for 3 microphones. The first 2 microphones require a gain of negative 2, but the third microphones require a gain of negative 3. What are the values of the input resistors if RF is equal to 10K? R1 is equal to R2 is equal to negative RF over high voltage gain 1 That's negative 10K divided by 2. That gives you a 5 kilo ohm resistor. R3, negative RF over AF3. That gives you minus 10K divided by negative 3. And that gives you a value of 3.3K. If a constant level is the input, the current is constant. The capacitor charges from a constant current and produces a ramp. The slope of the output is given by the equation delta V out over delta T is equal to negative V in over RIC. To sketch the output waveform, there you can see the waveform starts at 0 to plus 2 volts to negative 2 volts. So delta V out over delta T is equal to V in divided by RIC, and that gives you 2 volts divided by 10K multiplied by 1 microfarads. That gives you a 2 volts per millisecond. So V out, there you can see the waveform there. That's 2 volts RMS plus 1 volts to negative 1 volts. And that is how your output signal is going to look like. The output voltage of a differentiator is given by V out is negative Vc over T multiplied by RFC. So for example, given that the input below sketch the output wave for the differentiator, you see for instance where the output sets from negative 1 to plus 1. So V out is equal to negative Vc over T multiplied by RFC. That gives you negative 1 is your peak voltage or your capacitor voltage divided by 0.5 milliseconds multiplied by 10K multiplied by 0.1 microfarad, and that gives you a value of 2 volts. And there you can find the output waveform from plus 2 to minus 2. Hysteresis. What is hysteresis? Characteristics of a circuit in which two different trigger levels produces an offset or lag in the switching action. Smith trigger is a comparator with built-in hysteresis. Bounding is the process of limiting the output range of an amplifier or other circuits. An integrator is a circuit that produces an output that approximates the area under the curve of the input function. And then a differentiator is a circuit that produces an output that approximates the instantaneous rate of change of the input function. There's just a slide with all the formulas you basically need. The slide is also in the PowerPoint presentation PDF version that's been given to you before. So now let's look to a few homework exercises of chapter 13. I selected randomly some of the exercises there that I thought perhaps you can have some problems with. So let's start with section 13.1, number 1. The question says a certain op-amp has an open loop gain of 80,000. The maximum saturated output level of a device is plus minus 12 volts. When the DC supply voltage are plus minus 15 volts, if a differential voltage of 0.15 millivolts RMS is applied between the inputs, what is the peak-to-peak value of the output? The output peak is A open loop gain multiplied by V in. That's 80,000 multiplied by 0.15 millivolts multiplied by 1.414. And that is equal to 17 volts. Since 12 volts is the peak limit, the op-amp saturates. So V out peak to peak is equal to 24 volts with distortion due to clipping. Section 13.1, number 3, calculate the upper trigger point and the lower trigger point in the figure below. Show the voltage levels. We know that upper trigger point is the voltage divider rule, R2 divided by R1 plus R2 multiplied by your supplied voltage of 10 volts in this case, and that gives you 2.77 volts. Lower trigger point is basically negative 2.77 volts. Determine the hysteresis voltage for each comparator in the figure below. The maximum output levels are plus minus 11 volts. So let's first focus on circuit A. For circuit A, the upper trigger point, again, we applied the voltage divider rule, you get 3.88 volts. Lower trigger point is symmetrical to the upper trigger point, that's negative 3.88 volts. Hysteresis is the upper trigger point minus your lower trigger point at 3.88 minus 3.88. That gives you a value of 7.76 volts. Now focus on circuit B. Exactly the same formulas is being applied. You get the upper trigger point of 3.43 volts. Symmetrical lower trigger point is negative 3.43 volts. And your hysteresis work out to be 6.86 volts. Section 13.1, number 7, yes. A 6.2 V Zener diode is connected from the output to the inverting input in the figure below, with a cathode at the output. What are the positive and the negative output levels? When a Zener is forward biased, we know that V out, voltage divider rule, 18K divided by 18K plus 47K multiplied by V out, negative 0.7 volts because it's now in the forward bias mode. So V out is equal to 0.277 multiplied by V out minus 0.7. And V out is 1 minus 0.277, and that is equal to minus 0.7 volts. So V out, if you manipulate that, works out to be negative 0.7 divided by 1 minus 0.277. Your final answer there is negative 0.968 volts. And when the Zener is in reverse bias, V out is equal to 18K divided by 18K plus 47K multiplied by V out plus 6.2. That is now the Zener diode voltage there of 6.2. Use that formula. If you manipulate that formula, you will get that answer of V out is plus 6.2 volts divided by 1 minus 0.277. That gives me an answer of positive 8.57 volts. 13.1, number 8. Determine the output voltage waveform of a circuit. This particular comparator has both hysteresis and Zener bounding. The voltage across D1 and D2 is either direction is 4.7 plus 0.7 plus 5.4 volts. This is because one Zener is always forward bias with a drop of 0.7 volts, when the other one is in breakdown. The voltage at the inverting, the negative input of the op-amp input is V out is plus 5.4 volts or negative 5.4 volts. So the differential voltage is neglectable. The voltage at the non-inverting, the positive op-amp input is also V out is plus 5.4 volts, negative 5.4 volts. Therefore, we can say that VR2 is equal to V out minus V out plus minus brackets 4.7 volts plus 0.7. That VR2 is plus minus 5.4 volts. So IR2 is VR2 divided by R2. So that gives you, since a non-inverting input amplifier is neglectable, we know that IR2 is equal to IR3 is plus minus 114.893 microamps. So VR3 is equal to IR3 multiplied by R3. That gives you 114.893 microamps multiplied by 10. So your answer is plus 1.149 or minus 1.149 volts. V out is equal to VR3 plus VR2, and that's 1.149 volts plus 5.4. And that gives you a value of plus 6.549 or minus 6.549. The upper trigger point and the lower trigger point are as follows. V upper trigger point, R3 divided by R3 plus R2 multiplied by positive V out. That gives you 0.175 multiplied by plus 6.549. So upper trigger point is plus 1.146. And the lower trigger point, use exactly the same formula there, and you get hold of a value there of minus 6.549 volts. Plus 1.146 volts. Section 13.2, number 13. Find the output voltage when the input voltage show a free circuit diagram are applied to the scaling adder. What is the current through RF? First of all, we know that V out is negative RF over R1 multiplied by V in plus RF R2 multiplied by V2 plus RF over R3 multiplied by V3 plus RF over R4 multiplied by V4. If you substitute the values, you will find the value there of negative 3.57 volts. So IF is V out divided by RF. So that's 3.57 divided by 10K. IF works out to 357 microamps. Section 13.3, number 18. A triangular waveform with a peak-to-peak voltage of 2 volts and a period of 1 millisecond is applied to the differentiator in figure 13.70. A. What is the output voltage? V out plus minus RC multiplied by V peak to peak over T over 2. Substitute that values, you find the value there of plus minus 2.82 volts. And there you can see the output waveforms that you can expect in that particular case. 13.3, number 19. If we begin in position number 1, in figure 13.70b, the switch is thrown into position 2 and held there for 10 milliseconds. Then back to position 1 for 10 milliseconds and so forth. Sketch the resulting output waveform if its initial value is 0 volts. The saturated output level of op-amp are plus 12 volts, minus 12 volts. For 10 millisecond interval, when the switch is in position 2, basically we will determine delta V out over delta T is equal to negative V in over RC. That is negative 5 volts over 10K multiplied by 10 microfarads is equal to negative 5 over 0.1. That is equal to 50 volts per second, and that gives you negative 50 millivolts per millisecond. Delta V out is minus 50 millivolts per milliseconds multiplied by 10 milliseconds. That gives you minus 500 millivolts. That is equal to 0.5 volts. For the 10 milliseconds interval, when the switch is in position 1, exactly the same formula. It works out at plus 50 millivolts per millisecond. V out, look at plus 0.5 volts. And there you can see the circuit that you can expect, the output waveform and expect on the output of this particular integrated circuit. Section 13.4, number 22. The given ramp voltage are applied to the op-amp circuit in figure 13.3. Is the given output correct? If not, what is the problem? First of all, we work where V out is equal to RF divided by R, and that is equal to 0.25 volts. After 0.5 milliseconds, V out causes by V in 1 is equal to 0.25 multiplied by 5 over 2. That gives you a value of 0.625 volts. After 0.5 milliseconds, V out caused by V in 2 gives you 0.375 volts, and V in 3 gives you 2.25 volts. V in 4 gives you a value of negative 0.75 volts. So V out is equal to V in 1 plus V in 2 plus V in 3 plus V in 4, and that gives you a total value of 2.5 volts. And there you can see the output waveform, what you can expect, the correct output waveforms. So there you can see the output indicated in the circuit is minus 2.125. So V out error is V out total minus V out indicated, and your error voltage there is 0.375 volts, and 0.375 is basically a problem going to occur there where the output should be shown as above. So an open R2, V2 is missing, will produce the observed output, which is incorrect. Section 13.4, number 29. The question: design an integrator that will produce an output voltage with a slope of 100 volts per microsecond when the input voltage is a constant 5 volt. Specify the input frequency of a square wave with an amplitude of 5 volts that will result a plus 5 volts peak-to-peak triangle wave output. 100 millivolts per microsecond is equal to 5 volts divided by RIC. If I manipulate that formula, I get RIC multiplied by 100 millivolts divided by millivolts per microsecond divided by 5 volts. that gives you is equal to 1 divided by RIC. So IRC is equal to 5 volts divided by 100 millivolts per microsecond. So that gives you 50 microseconds. RI is 50 microseconds divided by C. So I choose C to be equal to 3,300 picofarads. Substitute that in that equation, RI, 50 microsecond divided by C. So RI is 50 microsecond divided by 3,300 picofarad. And that gives you a value of, for a 5 volt peak to peak triangle waveform, will give you T ramp is equal to T ramp down, T ramp up is equal to T ramp down, is 5 volts divided by 100 millivolts per microsecond, and that gives you 50 microseconds. T is equal to 2 times 50 microseconds, and that gives you 100 microseconds. Fin is equal to 1 divided by 100 microseconds, and that gives you 100 kilohertz.